interesting now. What we need is a mind twister, the courtesy of MIT. All right, that's something that I got from a guy who got his master's degree from MIT in computer science. All right, so one day, he's a friend of mine, computer scientist, so I was visiting him at work, and then for whatever reason, the conversation turned to physics. And he said, do you know that the tip of this falling pole, in this case, or stick, is going to accelerate at a larger rate than a falling ball from the same distance? I said, number one, no, I didn't know that. Number two, it wouldn't happen. I mean, I was like, that's straightforward. I said, everything is going to accelerate at the same rate under the influence of gravity. Whatever the acceleration of this one is, the tip is going to accelerate at the same rate. That's straightforward. It's common sense. He said, no. He said, the tip is going to accelerate at a larger rate than the ball will. I said, prove it. That's how we do it in physics. Okay, somebody makes a contrary statement, and then I say, prove it. And just convince me that that's correct. And in physics, then you sit on, and then somebody does a derivation, you go, okay, and then you either agree or disagree with it. Except the problem is this guy is not a physicist, he's a computer scientist. He doesn't quite have the same background as I do, obviously, so he's not going to be able to prove it, but he made an argument. He said, hey, listen, I can't prove it to you because, number one, I'm not a physicist. Number two, I took the course like 20 years earlier, or 30 years earlier, more like it, in this case, at MIT. And the reason why he was able to remember it was because of the weirdness of the conclusion. Evidently, his physics professor, did this on the board, and the conclusion was so contrary to what he thought was going to happen. It's just he remembered it because he thought everything would accelerate at the same rate, which means that whatever the speed of this ball is, the impact speed of this ball is, he thought the tip is also going to hit the ground at the same speed. Right? And then the professor says, no, they're not accelerating at the same rate. And all of a sudden, he does a mathematical proof of it. And then because it was just so contrary to what he was expecting, he just remembers it 30 years later. And then that becomes the conversation that we're having. So he was not able to prove it. And at least I knew that this guy remembers something which is weird, done by his university professor. Well, the guy is a physicist, obviously his professor. So if he could do it, I figured that I could do the same thing. So I decided to investigate. And here's what I came up with. This is a strange learning experience. Now, take a look at free fall. Either I'm right, because I'm a physicist, and this guy is a computer scientist, or I'm wrong, because the MIT physicist knows something that I don't, or I didn't. All right, so the best thing to do is just come up with an expression for free fall, final speed of free fall. Motion is going to be under the influence of gravity, so mechanical energy is going to be conserved. Initial mechanical energy is the same as the potential energy of the ball. Final mechanical energy is the same as the translational kinetic energy of the ball, the center mass. All right, so translational kinetic energy, the potential energy, electrons cancel, obviously, the algebra works itself out. It's the final equation. Okay, now stop at this point. But I'm correct when we solve it for the final velocity of the tip hitting the ground. If I'm correct, we get the same equation. All right, so when we do the work again, we should exactly get the same equation. So that's what we're going to do. Now we're going to check the state. We're going to come up with an expression for the final velocity of the rotational motion for the tip. So once again, growing air friction, mechanical energy is conserved. Final mechanical energy is going to be the rotational kinetic energy of the tip. Potential energy is the potential energy of the tip that we're looking at. And you just and then I remembered that we've done this problem already. Oh, so that meaningless exercise all of a sudden becomes meaningful. And I love how colorful the solution is. All right, so when you finish it up, this is the expression that you end up getting because we've done this problem before. I just set it up. Not the same. I mean, G is the same, L is the same, but the numbers are not the same. Immediately you realize that in rotational motion, the tip that's undergoing rotational motion is going to have a larger impact speed than the ball in free fall. All right, so the speed of the ball is going to be smaller than the rotational motion, the speed of the tip because of the rotational motion. In fact, when you turn this into a ratio, you take this and divide it by that, and you're able to cancel out the electrons. So it's going to give you square root of 3. All right, so square root of 3 is going to be 1.73. Okay, which means that the tip is moving 1.73 times faster than the ball. So which means that the tip is accelerating faster than the acceleration due to gravity. Oh, this was a good learning experience. It was an eye-opener that when you are dealing with rotational motion, unexpected things could happen, evidently. It's not like, because we've been dealing with linear motion. With rotational motion, there's some hidden gems in this. Why does that matter? Well, the reason why that matters is because that explains this. Guys, up to this point, right at this point, acceleration is going to be g. All right, anything before this point, the acceleration is going to be less than g. So the structure remains intact. And for this portion to fall in line with the rest of it, it needs to accelerate at a rate which is going to be larger than g. All right. Gravity can only allow things to fall at the rate of g, and for this to be able to fall at a rate larger than g, this needs to be properly reinforced in the sideways direction, so so that it would not break. So if this portion did not break, everything would be falling at a rate larger than gravitational acceleration. So it builds up stresses along this direction, and the structure is not properly reinforced in the sideways direction to keep the entire structure in one piece. So as a result, what happens? This section just breaks up. And this section is going to keep falling at the rate of g, 1g, the acceleration due to gravity. All right, so that's weird. A little thing that I end up learning because of that weird discussion, all of a sudden becomes the explanation as to why the chimneys break. Because this portion is accelerating at a rate of g. Anything below this is going to be accelerating at less than g, so the structure remains intact. For the rest of the structure to follow with this one, it has to have a proper reinforcement, so that it has to stay in one piece. Because it's not properly reinforced sideways, for sideways tension, it just picks up. Another mind twister. This is not from MIT. This is one of those things that this is just a chance discovery. All right, because I don't know why. I was just reading this physics experiment done by high school students. This is not MIT. This is not Cornell. This is not Harvard. This is high school. Okay, I don't know why how I found that. Somebody must have emailed it to me. High school physics experiment. So you got these kids doing this tiny little experiment with their cars. So what they do, they drive the car onto an icy surface. It's perfectly icy. So they hit that ice at 50 miles per hour and they lock up the brakes. These guys are using a radar gun. So they hit ice at 50 miles per hour. As soon as they lock up the brakes, they realize that the car actually sped up. It went from 50 miles per hour to say 50.1 or 2 miles per hour. So there's a little bit of a change in speed, small measurable change in speed. All right. So instead of car going at a constant speed when they lock up the brakes or slowing down, this car literally speeds up just a very little amount. Like you go from 50 to 50.1 or 2 miles per hour. Small but a significant change. So I'm reading it, and of course my initial impression that, oh, they goofed it up, something is wrong. I think there's a measurement error. All right, it didn't make sense. But then again, how could there be a measurement error? So it's a radar gun, guys. Look at the speed on the radar gun. They hit ice at 50 miles per hour. They lock up the brakes, and then it goes up to 50.1 or 50.2 miles per hour. Okay, they repeat a number of times. So this is what they discover. So how do you explain the increase in speed? My initial attempt at this one is, number one, I was skeptical initially. And then I said, what if this is true? If it's true, how do you explain it? And I wasn't able to come up with a good explanation at first. Then I noticed that there's something weird. Once again, it's a combination of linear motion that we've been so used to, and then combine it with the rotational motion. All of a sudden, some weirdness is start to happen that you need to explain. All right, so let me take you through my reasoning that you will agree with up to a certain point, and then something weird is going to happen. So when I say mind twisters, these are little mind twisters. The MIT thing was amazing. It was a great learning experience. And this is even a greater learning experience because it's coming from high school students. Some basic research, but man, there's some interesting stuff. All right, so it's got 4 tires, the wheels or whatever. All right, so they got center of mass, so the center of mass is gonna have a kinetic energy, so that's the translation of kinetic energy. Tires are rolling, you got 4 of them, so all 4 tires will have rotational kinetic energy. And obviously, you got on top of that, you got the mass of the car included, masses of the tires, blah blah blah. All right, so if it's a perfectly frictionless surface, it's a surface. There's no such thing about it. It's just go with that assumption. Okay, so everything is going to be assumption dependent. All right, so for you to be able to change the kinetic energy of the car, you have to do work on the car. All right, so which means that you have to transfer energy to the car. The only way you can transfer energy to the car by applying a force that could cause displacement. So if you're using the accelerator, obviously there's going to be drive force. All right, if you're using the brakes, there's going to be frictional force. So either way, it's either you're going to gain kinetic energy or you will lose kinetic energy. Okay, so I'll make the assumption that this is a perfectly frictionless surface. It's an assumption. It's an underlying assumption. If that's the case, there's absolutely no force acting on it on the linear direction. So there's no change in kinetic energy. So in the absence of an external force, you maintain your initial motion. Velocity remains constant. No change in kinetic energy. All right, that was my first assessment. I said, there's no way this thing is going to speed up in the absence of an external force. My next assessment was, if there's a force acting on it, it's the frictional force. I understand that that's an icy surface. So if anything, the car is going to go from 50 miles per hour to maybe about 49 miles per hour. If there's a change in speed, it's going to slow down. It cannot speed up. And so that's the way I was looking at it. So let's go with the assumption that the net force acting on is 0. There's no change in kinetic energy. So which means that final kinetic energy and the initial kinetic energies will be the same. All of a sudden, you have to remember that the kinetic energy is a combination of translational and rotational kinetic energies. So these tires are rotating, and the centers of mass of these tires are translating in forward direction. But as soon as you lock up the brakes, what happens is this rotational kinetic energy and the translational kinetic energy will become total translational kinetic energy. What that means is this rotational kinetic energy is going to turn into the translational kinetic energy of the tires. Let me make that point clear one more time. Okay, so kinetic energy is going to be constant before and after you apply the brakes. All right, before you apply the brakes, kinetic energy, one part translational kinetic energy, the other part is going to be rotational kinetic energy. So it's a combination of both. So what happens when you apply the brakes? This is going to go down, and this is going to go up. So the translational kinetic energy is going to go up, which means that the translational speed, the speed of the vehicle is going to go up. And then I've done the calculations. How much would that go up? It's going to go up literally. The vehicle is going to go from 50 miles per hour to 50.1 or 50.2 miles per hour. Numbers check out. I'm thinking, wow, this is weird. I didn't expect that. All right. So when you have two different motions, the translational motion of the center of mass and rotational motion gets converted into the translational motion. So this energy gets transferred into rotational energy gets transferred into the translational energy. So as a result, the car literally speeds up just a little bit. All right. This was a mind-blowing experience because I didn't realize there was so much more physics in these little experiments. So this was a good learning experience. The next one is, speaking of discovering stuff. Oh my God. Galileo, father of science. All right, so Galileo is known as the father of science because of the simple reason that he said, hey, if you got a theory, express it in such a way that it makes measurable predictions in essence. All right, so it needs to make measurable predictions. So you test the predictions. If the prediction is correct, the theory is good. If the prediction is incorrect, obviously the theory is incorrect. So free fall, everything falls at the same rate. So he's slowing the motion down. He's using an incline. So he's rolling these objects down. So they're slowing down. So he can measure the distances in every single 1 unit of time intervals. But the underlying assumption is that everything is going to be rolling at the same rate. So the question is, will everything roll at the same rate?